So welcome one and all to the latest installment of the Brooklyn Quant Experience, so BQE. And we were originally scheduled to have Professor Kim Weston from Rutgers University present tonight, but unfortunately she came down with a cold. So we asked Professor Sturm to step in, and he kindly agreed. So Professor Sturm is visiting at NYU Tandon, and I saw him give this talk recently at Fordham, and I really liked it. And I have to say I didn't understand everything, so I wanted to hear it again. So I'd like to read Professor Sturm's bio. So he's associate professor of mathematical sciences at Worcester Polytechnic Institute. I think I said that badly. Anyway, WPI in Massachusetts. And currently spending a sabbatical at the Chinese University of Hong Kong and here at NYU Tandon. So after obtaining his PhD in math from TU Berlin in Germany, he became a postdoc research associate and lecturer at the Department of Operations Research and Financial Engineering at Princeton University before joining WPI as a faculty member. Professor Sturm's research covers many different areas of financial mathematics, but he's interested also in stochastic modeling in general, such as applications to climate science. In finance, his work is devoted in particular to questions of value adjustments for derivative securities, this is called XVAs, optimal portfolio selection, and systemic risk in financial markets. Professor Sturm.
Thank you, Peter. Now, I have to say I have a really great time here and a great semester at NYU, so I'm more than happy to step in. And of course, I cannot give you what Professor Weston would have given you, but I think it's an interesting talk, and I think it has many different levels, so I think there's a core message, which is relatively easy to understand, and then different levels of detail. So, to set it up on a very big scale. So, what we are concerned with is one of the classical questions of quantitative finance. Now, quantitative finance basically is either derivatives pricing or portfolio management, and well, maybe a little bit risk management. But these are the three big topics, and I will devote this to one of them, portfolio management. And we take, however, a little bit a different angle than what most people are doing, both in academia and industry, and I will tell you why. But before I do this, I should point out that this is not only work by myself, but with two collaborators. One is Mauricio Elizalde, who is currently a PhD student in Madrid at University Autónoma. And the other one is Carole Bernard. She is a professor in finance at the Grenoble Business School in France. And we worked together on different parts of the talk. Ours are, of course, all male. As I said, we are doing things maybe a little bit different than what you might have experienced somewhere else. Let's maybe first take a very big step back and let's think in general about what is portfolio optimization and how to do it. Well, what is portfolio optimization is, I think, a relatively easy question. The question is usually you have a certain amount of money and you want to invest it optimally in different assets in a way which is good for you. And well, what we have to discuss is what means it is good for you. And in general, it is good for you can be understood in many different ways. On a very big level, one could say, either we try to find some general optimality principle, which has nothing to do with you and your personal preferences, but just tries to say, let's do the best, whatever the best is in general. And things like this are, for instance, the so-called Kelly criterion and Kelly betting. But much more common is another approach, and this is an approach who tries to take the preferences of an investor into account. Well, there are many ways to do it. There is, for instance, Markowitz's approach, or after that's the CAPM, which basically relies on risk aversion and an understanding of, well, there is a trade-off between risk and variance in a sense. Well, you want to have a return as high as possible and a risk as small as possible, and you cannot achieve both at the same time, and you have to juggle around between these two. More general and more in particular used in academia, in particular in business schools and finance departments, is a different approach, a more general approach, which is using so-called utility functions, which means that the preferences of a given investor are encoded in a function which is called utility function, and then this is used to determine optimal investment strategies. This is actually something what is a very, very long history, much longer than everything else we know of financial math. Well, usually if we think about financial math, we think about developments which happened since the late 60s, early 70s. No, our founding fathers, Merton, Schultz, Fisher, like Schultz formula, Merton optimal investment, these were things which were developed 50 to 60 years ago. If you think really historically about financial math, maybe somebody comes up and tells you, well, I heard about this guy Bachelier in France who did already in 1900 a thesis on how to price options. But this is basically the oldest what people usually think. Utility functions are much older. This Swiss guy, Daniel Bernoulli, a child of one very famous family of mathematicians in Switzerland, he introduced these utility functions already in the first half of the 18th century. So how did he came to do this? Well, the big thing, and it was at this time less thought about investing but more about gambling, is this problem which is known as the St. Petersburg paradox. Don't know if you have heard it, but if you just think about a simple game, you flip a coin, you can bet, and if you get heads, you get what you have bet plus the same amount, so hence you're doubling. Or if you're losing, then you just lose what you have bet. And this St. Petersburg paradox, a doubling strategy, tells you, well, there is a great way to always make a gain in this game. Since you play for $1, if you win, you are happy, you go out with $1 and you won. If you're losing, what are you doing? You play, but now with betting $2. Well, if you win $2. The first game you lost $1, so in total you're still $1 up. You go out. Well, if you're losing, then it's not good, since first you lost $1, now you lost $2, so you are negative $3, but you are now starting to bet $4. If you're betting $4 and you win, you're in total +1. If you're losing, well, you can just continue to increase your bet size. You bet for 8, you bet for 16, and well, you know, a coin flip cannot forever show tails. Sometimes heads has to appear, and hence, at some point, you will have $1 and you can move on. Well, this is something which doesn't seem very plausible, and the reason why it's not very plausible for us nowadays is maybe to say, well, we have not an infinite amount of credit. Playing for 8 for $16 is maybe something what I'm happy to do. And $1,024 I have maybe already to look on my bank account how things are doing. And if I go some powers of 2 up, my bank will say, no, you don't have this money, we don't give you this money to bet. So the strategy will. However, he thought in a different way about it. And actually, this here is his original drawing of this, what he calls a utility function. And he says, well, in general, $1 is not $1. How you value $1 depends very much on how much money you already have. If you're very rich, one additional dollar increases your happiness only a little bit. But if you're very poor and you have $0, getting $1 is absolutely great. And he explains this on a very nice story. He says, a very poor man who walks on the street and who finds somewhere on the ground a lottery ticket. This lottery ticket is already filled out and paid for, and it's a very simple lottery ticket. Either it wins with probability 50%, and then you get $10 million. Or with 50%, you lose all the money. Well, this is great, since on average this poor guy gets, in this case for free, $5 million. But now a rich man comes along, and he makes this poor guy, he sees this poor guy found a lottery ticket, and since he's a nice rich man, he doesn't call the police and take it for himself. No, he makes the poor guy an offer and says, well, I would be willing to buy this ticket for $4 million. And the poor guy agrees and says, yes, here's the ticket, I take the $4 million. Well, why are the two people making this deal? Well, for the poor guy, the situation is, well, maybe with 50% probability I'm very rich and I have $10 million, but with 50% probability I might have absolutely nothing and I have still to starve as all the other days before. So it's much better to have $4 million for sure, which from his perspective is not much difference than $10 million. It's just a huge amount of money. And so this is a good deal for him, and he knows basically he can eat very well for the rest of his life and have a nice housing. For the rich guy, however, he doesn't care about this money. He has already a couple of $1 billion, so having another either 10 or 4 is not a big difference. But he counts like this. Well, on average, this ticket gives me $5 million. I pay $4 million. So on average, I made a $1 million gain of it. So it makes sense for me. So this is a story which makes for both of the guys sense. And to get from this story to a mathematical representation, he said, well, people have usually a utility function which looks like this, which tells you about how much you value a certain amount of money. And this function is on the one hand side increasing, but that such a function is increasing is a little bit clear, no? Everybody prefers more money over less. Well, nobody will tell you I prefer $3 over 5. But the other feature is not completely clear, and this is that this function is convex. Concave, thank you. If it's convex, then we should be really bad. No, it's concave. And this is exactly what represents that your amount of money or your amount of wealth, which is on the x-axis, if this is relatively small, the gain of happiness, this utility function measures something like your happiness with money, your gain from an additional dollar is much higher than if your wealth is very high, then going an additional dollar to the right on the x-axis moves the y-axis up only a little bit. And this is the basic concept how economists measure preferences of people. So use utility functions to represent preferences of people. Bernoulli was the first one, and this has then been done by von Neumann, which you might know as one of the parents of the modern computer, and Oscar Morgenstern, which is a very well-known economist. They came up with an axiomatic theory, and they could show, well, as long as people have somehow consistent preferences, then there has to be such a concave utility function representing the preferences, and the other way around. Each such a concave utility function corresponds to a reasonable set of preferences. And this has been since the start of modern portfolio theory, and Bob Merton, which was also one of the inventors of the Black-Scholes-Merton formula. He also came up in the late 60s with this idea using utility functions for portfolio optimization, and since then there are academically, I think if I say a couple of thousand papers, I'm underestimating it. I would say a couple of 10,000 papers treating different variations on this problem. Now, this is all nice and good. I don't want to talk too much about this further. Why? Well, since there is actually a lot of criticism on this kind of utility theory. And I want to discuss mainly 2 points. The first one is maybe the most common one, which was first developed mostly by people who are coming from psychology, but have now really found a large foothold in economics departments, and this is what is in general called behavioral finance. Let's study not what people should do, but what people are really doing. And there were actually also Merton won a Nobel Prize, but also in behavioral finance, a couple of people won Nobel Prizes for work on this. Kahneman, for instance, he is one of the first one who did it. And there was also another one for Richard Thaler, obviously. So this is very something on hope. You can win Nobel Prizes with this stuff. But at the end, all what they are saying is we try to measure what people are really doing, and what people are really doing doesn't look like this nice concave-shaped function. What people are really doing is many things, but there are a couple of patterns. And the one pattern is, well, for winning money, this is something like pretty reasonable on concave function, but for losing money, most people behave like it would be a convex utility function. What does this mean? Well, if they lose some money, instead of just cutting the losses, they start, as in the St. Petersburg paradox, to gamble. This happens in particular in financial industry, that traders who make big losses try to hide these losses and get additional money to make bigger and bigger bets to get out of the situation, to not be fired. And if you go through the list of big trading scandals, I think at least half of them can be explained by such a behavior, that people try to overcome the losses that they get from Liam Neeson, Neeson is the actor, Nick Leeson, the Bearing Banks over Jérôme Kerviel, over the London Whale. You have very often this kind of behavior. So this is the one thing. The other thing is to say also in reality, so you need a different shape of utility function, but in reality also people don't see all kinds of events equally, and in particular they think about events which are very severe, very extreme, and very unlikely. That gives them a higher probability than what's happening in reality. And so you can even not do classical probability theory, and you need something what is called Choquet integrals, and yes, that's also a big bunch. But I personally think this is not, for what we want to do, portfolio optimization, I don't think this is a very valid line of criticism. Why? Since I actually don't care about what people, which stupid things people actually do. People do stupid things, but I want to give them advice, and I don't want to give them advice to do the stupid things they're doing always, no. I want to give them advice how they can do better. I want to give them rational advice. So if my goal is not just describing what people are doing, but giving them advice, there's a good argument to make that this is a nice line of what people are doing in reality, but if I want to give them advice, this is actually sound advice. However, there is another problem, which I actually think is a little bit a bigger problem, and this is theoretically everybody of you should have such a utility function, but how to find it out? There is no good, reliable way to find out utility functions or even risk aversions of people. In a way, well, there are many people who try different things, people giving questionnaires, how do they react in a certain situation with money to get some approximation. What I know, all of this is not very reliable, and if people do it again in a slightly different setup, something completely different is coming out. So, the goal is can we do something about this? Can we think a little bit different about investing instead of having this utility function theory? Can we do something else to get around this problem, finding out the people's utility functions? What I say is, I like the theory, and if you come with your utility functions and tell me, well, I have found out this is my utility function, please invest for me, I say, great, I can do it. But realistically, most people cannot come up with the utility function. So what can we do instead of getting utility functions of people? And this is something which not I have invented, but another great mind, another Nobel Prize winner, Bill Sharp. Bill Sharp might be somebody you have heard of. Most likely that somewhere you heard about the Sharp ratio. You might also heard about that he was one of the main guys pushing CAPM and index investing in general together with Jim Bogle. And he came up with this idea, what he calls the distribution builder. And he's coming together with some co-authors, Goldstein, who is a psychologist, Light and Johnson. And they come exactly from the point, investors are notoriously bad in estimating the utility function. Try to instead to get a way which is more direct to find out how people react towards risk. And specifically, they may choose a much more direct way. They say, okay, we fix the time horizon of your investment, let's say typically for your retirement. You have a certain distribution of wealth. Well, since investing is always random, you cannot guarantee a certain amount. All what you can do is a certain distribution. And they start there with the distribution and then say, well, if the customer gives me a distribution, I can find out what is the minimal amount of money I need to get this distribution. And I will tell a little bit more in details a little bit in a second. But I would say this is his approach, and so far there exists not much literature about it. So there are the papers which he himself has done, as far as I know, in his own investing firm. He is doing this or similar concepts to find it out, but more academically, I know only one paper of Philip Monin who worked on this, and otherwise this is something that is a little bit on the sidelines. I tried a little bit to resurrect it and make you aware that I think this is something that is very interesting.
Yeah.
And to understand a little bit better what is going on, let's look on what Sharp himself has written. He has written a very, very nice book. He gave a series of lectures over at Princeton and wrote from these a book, Investors and Markets. It's very understandably written, a lot of intuition built on simulation. It's over in the library if somebody wants to look on it. I like it a lot. I read it only a couple of months ago, the first time really completely, and I like his thinking a lot, and I got a lot of insights. First, I want just to focus on one paragraph, what he has written. In a complete market setting, the usual way, and the usual way is exactly utility functions, but the same would be true for, let's say, CAPM or Markowitz model. Well, what are the ingredients? Well, the one thing is you have a budget. You know how much money you have that you can invest. I think this is clear. Well, we know what are the asset prices, how we model stocks and bonds and other assets in which we want to invest behave. Well, we have a model. Models can be much different. Can be a simple geometric bounded motion by Scholz model. Can be discrete time. Can be very complicated jumping stochastic volatility models. But we have these things, and we have preferences. Preferences means usually either utility functions or measures of risk aversion. And then classical theory tells you always these are the ingredients. With these ingredients we can come up with an optimal investment strategy for you. This optimal investment strategy tells you how to invest. What is the result of this optimal investment strategy? Well, depending on the dynamics of the prices, you will end up with some distribution of wealth at your retirement. And which distribution depends very much on how your investment strategy is. And he says, well, the big problem is we have a very hard time to find out people's preferences. So let's try to invert this whole procedure. And well, we don't worry about the budget. Everybody knows how much money they have, at least they hope. And if they don't know, then they have enough money and we don't have to worry about them. Asset prices, well, we have typical models for asset prices. There will also not much around. But we will invert this too. We will try to get from the people directly the information about which distributions they would like to have at the retirement. And we then will, from this distribution, figure out what is the best way to invest. And as a side product, find out also about the preferences in the people in a more classical way, for instance, finding the utility function.
Yeah, so that point, the last one, I mean, it may well be that they pick a distribution to go find the so-called utility function and it's not concave. Do you agree?
No.
No? You got
Well,
it. All right.
I agree do not agree as long as we have a complete market. As long as we have a complete market, we will always be able to find a concave utility function which corresponds to the distribution and the chosen by the people. I come to it in 1 minute.
Okay. So, all right. You're going to come to it? Okay.
I will come to it,
yeah. Okay, sorry.
Okay, just to walk you a little bit through how this works practically, Sharp has on his website actually a pretty nice model. And this is how people actually work with this distribution. It looks like a little bit like a game of Tetris or so. So you have a lot of these small blocks. 100 blocks, but doesn't matter how many there are really, and you can just move these blocks around. And you have a level of 100% of your original wealth, and here's just a scale of how much you want. You might have some lower level if you want to implement it, you might have some reference point, but the key point is you can just move around these blocks, and what is happening behind this distribution builder is when you're moving things in a certain situation, behind this picture, there's a calculation machine who calculates exactly of how much your budget is used to get you this specific distribution. And well, you want to be close to 100%. And if you are below 100%, well, then there's some money which you're not using for investments and it's throwing money away. And well, if you are above 100% of your budget, well, then you cannot afford it. So you can never be above, and you should not be too much below.
So is it implicit here markets are complete in this calculation?
Yes.
Okay. That helps. But I still have a question anyway. So what I'm thinking is two random variables that are distinct from each other can have the same probability distribution.
Yes.
Okay. So they pick a distribution, but how do we go from that distribution to one of the two random variables? It's not obvious.
Also, this question is coming in 2 slides from now.
Okay.
But I recognize this is exactly the great question what is behind. People choose here distributions, not random variables. You're usually used to deal with random variables. If you're doing, I don't know, hedging options or so, you know exactly what is the random variable. It's the maturity of the option. Here we don't have a random variable, we have only a distribution. So there are many random variables which have the same distribution. And not all random variables have the same cost of hedges and have the same price.
Mm-hmm.
So the question is, how can we find the cheapest random variable which has exactly this distribution?
Okay. Okay, that helps.
This is exactly the question we have.
Okay, thank you. Okay.
And this is what is happening behind it.
And that's where the advice is coming in, right? Like, let's say the form of the advice is this is the cheapest way to get what you're after.
And then gives you also a hedging strategy.
Okay.
Well, as soon as you have a random variable you want to achieve in a complete market, at least formally, you can write down a hedging strategy.
Okay.
Why? Well, under the risk neutral measure, you want anyway to be a martingale. You have a martingale representation theorem, and you have explicit forms of the martingale representation theorem which can write you down basically what is your delta with which you should hedge to get this final.
You're calling it hedging, but you mean like replication, because there's nothing to hedge. Okay, so yeah, so I know what you mean now.
Replicating the distributions makes it better.
Yeah.
Can you just clarify what is the random variable? I mean, I see the distribution. What's the random variable you're talking about?
The lowest cost random variable that delivers that distribution.
This is
Yeah,
basically.
it's a real valued random variable.
Yeah.
Okay, let's put it like this: a real value. Yeah.
Yeah.
This is only the distribution output. There's something else which I didn't tell you about. Of course, we have to some assumption about the model. We have to say what is our specific complete market model. To make things simple, let's just say we're living in a Black-Scholes world. No, we have a stock price which is a geometric Brownian motion, and some bond which we can invest in. Then these random variables behind it are all random variables I can achieve by hedging in this market and having exactly this distribution at the end. At the end, it doesn't matter as long as it's some continuous market model. We can also do it with discrete, but then you have just to look that everything is fine enough. If it's continuous, you can basically always do it. However, the specific price will depend, of course, on the specific model that you're using.
So is there some functional of this thing?
Yes. We're coming in one moment to this more mathematical details. I just want first to discuss the general understanding that we are all on a page what we want to do, and then I will space during the talk some half more and more up, okay?
Yeah.
So far, is everybody comfortable where we are on a big picture level? Okay. Then let's try to do a little bit more math. So, what is going on? For the moment, we will just assume we are in a complete market. Well, what does it mean that a market is complete? Well, informally, it means we can hedge all the risk what is possible in the market. Mathematically, it means, at least at first order, there exists an equivalent martingale measure, a unique one. There exists a unique measure Q, under which the market is risk neutral. I don't write this measure Q, I just write here the pricing kernel psi. This is a little bit a question from where you occur coming, but if you are more coming from the martingale measure crowd, then think just about psi is dq over dt. If this is more comfortable. If not, then it's psi, or at least this is the case when you assume zero interest rate. If you have another interest rate, then you want to discount it. But discounting is not a big issue, so I just usually assume I is equal to 0. These things you get easily.
It's getting to be a very good assumption.
Okay, what we want to do is, we assume there is this complete market model. If you want something specific, just think about Black-Scholes. And I think people prefer to call it the Samuelson model, since Black-Scholes is option pricing and geometric Brownian motion is Samuelson, but I think informal Black-Scholes is fine. Well, what you want to do is, you want to find a random variable which has exactly this distribution your client gave you with the distribution. What does this mean? You want to find one random variable, and you take the minimum of all of them which have exactly this distribution which is specified. So f, the CDF basically of the random variable comes from the client. And then we want to find the cheapest way to hedge. Well, what is the cheapest way to hedge in a complete market? Well, just the expectation under the risk-neutral measure. And well, what is an expectation under a risk-neutral measure? Well, this is just dq of x, which is nothing else than e of x times dq over dp, which is just in my notation here, e of x times xi.
Yeah. Let me make a comment.
Yeah.
So this approach of sharps actually reminds me of something in the probability literature called the optimal stopping problem for score-hod optimal stopping problem.
Yeah.
I don't know if you're familiar with it, but in that
Vaguely.
Okay. I'll just
So
tell
I
you
know what it is,
roughly
but
what it
I'm
is.
not an expert.
I'll just tell you roughly what it is. So for score-hod, someone has to give a probability distribution, and it has to have zero mean the way score-hod thinks, okay, because he's working on the whole real line. And then you have to run a grounding motion, but you have a stopping time that you supply, and then you demand that the stopped grounding motion have this distribution that you're starting from. So I'm just thinking it's pretty close in spirit to the way Sharp's thinking, in that Sharp needs a market model, and for score-hod it's standard ground motion. Okay, and that both people start with a distribution that's sort of given to them, and then they try to create it, though by different mechanisms. Let's say for Sharp it's via portfolio construction, whereas for score-hod there's only one kind of risky asset, so to speak, and it's when you get out of it. So it's sort of timing as opposed to portfolio construction. So anyway, I'm just saying they're similar. So it's interesting to think about.
Okay, so this is the problem. What you want to do, you can also write it differently. You can just say this is nothing else than a cost function. No, this is the cost of a specific random variable x, and then you want just to minimize the costs by taking the infimum over all random variables which have this specific distribution. Now, how can you solve this problem? There exists a nice result which is called the Fréchet-Höffding bounds in probability theory, but let's say I did something much simpler. Peter gave me an idea about this, and this tells you can write this optimal random variable, the random variable is minimizing this functional, as this form. You take just the quantal function, the inverse CDF of what you want, and then you take 1 minus the CDF of the pricing kernel applied to the pricing kernel. So what's going on here? What is going on here is a very simple idea which is called Chebyshev's inequality.
Mm-hmm.
Chebyshev's inequality tells you just if you have two...
Gotta be careful, because there's two Chebyshev's inequalities.
It's not the probabilistic Chebyshev inequality, it is the
For sums. I think.
number theory or some Chebyshev sum inequality.
Chebyshev's inequality for sums, I think it's.
Well, you have two ordered sequences of numbers, a1 to an, and a second one, b1, b2 to bn. All what we care about, they are numbered, and there's the same amount, there's ordered, and there's the same amount of numbers. And then the question is, I want to make a sum of a product. I want to make a sum over some ai, and then I take some other b, let's say sigma of I, some permutation of the index of I, and I want to sum over all I. Meaning either I take a1, b2 plus b1 times a3 plus a7 times b8 and so on. And then the question is, in which way do I have to order the sequences that I get either the maximal amount or the minimal amount? This is exactly what Chebyshev's inequality tells you. This tells you the sum is always the largest if you sum up the two in a monotonic way. So you're summing up AI times BI, I equal to 1 to n, and it is always the smallest if you are summing them up in what is called a counter-monotonic way. Meaning you're pairing the largest A with the smallest B, the second largest A with the second smallest B, and so on. So if we write the formula, this is AI B n minus I plus 1, I equal 1 up to n. So basic message is just if I order them in the same way, I'm maximal. If I order them in an opposite way, I'm minimal. And this can easily be generalized from sums to general random variables. If you have two random variables and have an expectation of them, then it turns out it is always the largest if psi and x are basically ordered in the same way, meaning when psi is large, also x should be large, and if xi is small, also x should be small. And it is the smallest when x is large, then psi is small, and the other way around, if psi is large, x is small. This is what is called counter-monotonic. And I can find the counter-monotonic random variable explicitly. Why? What is going on here? First of all, I know if I want to have a random variable with a CDFF, what I can do is I can just take a general uniform random variable and I can apply this CDF, let's say, of x to it, and I know this has exactly the distribution of x I want. No? This is something what you're very often using if you implement things in Monte Carlo and want to find Monte Carlo for distribution where your Python or C has not implemented the distribution. Well, so this is a uniform distribution. But this uniform distribution, well, you want to have a uniform distribution, this is a uniform distribution. If you apply a CDF to the random variable itself, you have a uniform distribution. But this is a bad uniform distribution, since a CDF is increasing. If you have a function, but this is also an increasing function, if you would have not this term here, you would have an increasing function of an increasing function of psi, which means that what you get out is ordered exactly in the same way as psi. This is bad. We want to have to order it in the opposite way. Well,
Yeah.
there's a cheap trick.
So just the meaning of F inverse is of as opposed to times 1 minus.
Yes, of.
Okay,
This
that's
is
fine.
this
Okay.
is a function
That's fine.
applied to
Yeah.
a random variable.
Okay, that's good.
Well, if I have a uniform, standard uniform random variable on the interval 0, 1, great news. 1 minus this uniform random variable is again a uniform random variable.
Okay.
And it changes exactly the order here now. This means now if psi is large, this random variable is small and the other way around. This means my optimal random variable among all the random variables which have this distribution can be calculated. All what I need to know is what is the pricing kernel in my market. Well, Black-Scholes market, you know this.
Yeah.
This is just coming from your Kirsanov transform.
Right.
Then I apply the CDF to it, apply the inverse function of what my client is giving me with the model, and I have the random variable what I need. Well, if I have a random variable, we are in a setting where we are hopefully very comfortable and we can just hedge the random variable in the same way as we hedge any kind of European option.
Yeah. Was this in the Sharp paper?
No.
Or this is yours?
I would credit mostly Carol Bernard and Stephan van Duffel for doing it. I don't think they've written it exactly in the same way down, but I would say this is where I learned this way of thinking about it.
Okay.
Sharp hasn't written it in this way.
Okay. Thank you.
I assume he's aware of it, but I don't think he has written it mathematically as this.
Okay.
Okay, but Message is this problem, which looked first very esoteric, is being transformed in something what you can do relatively easily by finding this esoteric problem, optimizing with a given distribution by, well, in a complete market I can tell you exactly what is the random variable among all random variables which have this distribution, which is the cheapest to hedge, and of course this is the one with which you want to target with your investment strategy. Okay? So this is the solution for the complete market problem.
Yeah, so, and getting back to, like what happens, like why is somebody with a so-called, like a risk lover, somehow excluded here? Because you were saying the utility function you get out of this has to be concave. So, you know, say someone actually is, let's say the way Quant and Tversky argue, let's say for the upside maybe they are concave, but the downside they're convex. So, you know, it seems that they can't play this, they can't participate. Okay, I'm wondering, can they participate? Like, can advice be given to them, or is it that, you know, only if you have a concave utility function can we do this for you?
Well, I would quote with something which came into my mind, which is a very nice mathematical inside joke. Groups as men are measured by their actions. So if somebody is risk-seeking or not, from this perspective, we don't know it. All what we know is the terminal distribution at the end which they come up.
Right.
I cannot get into the mind of people if they were risk-seeking or not what they can. What I will show you on the next slide is I can, however, find a very reasonable person which would come up exactly with the same solution. Maybe this guy is crazy, but I find you a gal who is very rational and who would do exactly the same thing.
Okay. Okay. So the real statement is there exists a concave utility function
That people behave exactly in this way.
Yes, right. But let's say, so I think you're saying if somebody doesn't have concave utility, it's still okay. I mean, they supply the F here. Let's say we use a market model with actuals is fine to get psi. And we do the calculation, and now we know the random variable that they should be trying to replicate as a result.
Okay, so I completely agree, but I want to make things clear at this moment. What we assume, we're assuming actually two things. The first thing I think we said in the beginning is it's very clear, everybody wants more money than less.
Yeah.
We don't assume that people are so foolish that they prefer $3 over
Like
$5.
that.
More money is better, or at least not worse than less money. I think this is something what we have to assume.
Sure.
And I think on this we don't have to discuss much. The second assumption is implicitly clear here, but we should nevertheless discuss it a little bit. And this is only the distribution matters. This says something, of course. This says only I care about the distribution, but this means I don't care about the state of the market. If you're an investor who says, well, I want not only invest in a way for a distribution, but I want to be also sure that if the market is crashing, I'm doing particularly well, and however, when the market is doing very well, I don't care much about, then this cannot be captured here, since all what we are saying, only the distribution matters.
Yeah.
Nothing else.
I think it's a big
This is
help.
not a revolutionary way to think, since this is what you're doing when you're a utility function, this is what you're doing when you're CAPM, this is what you're doing when you're Markowitz, this is even what you're doing Kelly. All these things are state independent. So that I'm also here state independent is not anything what is very esoteric, it's just a mainstream assumption, but I think we should be clear that it's an assumption, since usually people don't think about this assumption.
Okay.
But as soon as you have these two assumptions, you can find exactly a utility function meaning a rational Gel who is doing exactly this. This is actually the next result what I have here. And this is just a combination of what we have here seen and a classical result from portfolio theory, which is called dual representation. I don't want to get in all the details, but we have just seen we can find the optimal random variable in this way. This is just what I have written down here as a consequence of this simple Chebyshev idea. On the other hand side, classical duality theory tells you can write this psi star also as an inverse of a utility function of some constant times the pricing kernel, and the constant is exactly determined by your budget constraints that you can afford this distribution. So this is what classical theory tells you. This is what Sharp and Benign for Düffel and I'm telling you. And hence, if this here is this, and this here is this, well, also red has to be blue, no?
Yeah, so the main point here is U is concave, right?
Exactly.
Okay.
And if you have, this holds true for any concave utility function. If you have a concave utility function, you can write psi star in this way.
Okay.
This is hence a generic answer. They say, I have any rational investor with a concave utility function, then I can write the optimal portfolio in this way. And I have just shown you we can write the optimal portfolio in this way. Hence, we can say red is equal to blue and solve everything for you.
Yeah. Now there's some degree of indeterminacy. I'm thinking it might be that C in the lower limit of the integral, which is fine. I just want to understand what it is. So, like, you're not saying that there's a unique concave utility function. I think you're saying there's a family of unique concave utility functions up to scale, let's say, or something like that.
This is some, I agree, but this is something what is completely true in general.
Yeah.
Utility functions are always unique only up to affine transformations.
Increasing affine transformations.
Increasing affine transformations, to be clear. What does this mean? Well, you can shift things up and down, and you can multiply them with a positive number, and it doesn't change, say, investor behavior, since you're basically just changing scales.
Yeah, so over here,
And this is exactly encoded in this C.
yeah,
This C tells you how much you are shifting a utility function up or down.
yeah, so, okay, that's fine. So that's my answer to my question. So then but the other thing, the increasing part of that is sort of determined, it sounds like.
Well, this follows automatically. So you can check that if you have this function
Mm-hmm.
given as an integral, well, you're integrating over a positive function, hence you will be increasing for sure.
Yeah,
You can also check that this function is actually a decreasing function. Why? Well, since we said we are choosing these things exactly in this way, hence this function here is increasing, this function here is decreasing. We apply an increasing function to it, so this is still a decreasing function.
okay,
If I integrate over a decreasing function, I get exactly a concave function.
yeah, that's true.
So this function u is automatically increasing.
Yeah, so I'm
It is
saying,
automatically concave. It's
Right.
automatically differentiable. It satisfies automatically some additional condition like in other. The only thing what it does not satisfy compared to classical theory, it's not strictly concave.
okay,
It could be that this function here is for some part constant, and if this function here is constant, this function here will be concave but not strictly concave. But otherwise it satisfies all the, it's basically a limiting case of the classical theory where you don't require that concavity is strict.
so, risk neutral, so it could turn out that it's actually a risk neutral, so a linear utility function?
No.
Did that turn out? No? So you said it's like not strictly concave, and now I'm wondering, so could it actually just be a linear utility function?
No, it can be piecewise linear,
Okay.
but it cannot be linear overall.
All right. Thanks.
Can't fall directly from the question of CDFs.
Okay.
Basically, otherwise your CDF would in some way degenerate.
Okay.
But as long as you assume you have classical CDFs and not any degenerate CDFs, then we don't have any issues.
Okay. Thank you.
Okay?
Uh-huh.
So basically this is, I would say, this here is the main result in the theory of Sharp. And this here is the main result how you can connect it to the classical theory of utility, saying, well,